In this video, I would like to talk about the formal definition of limit. On the board, you actually see our first notion of limit and then the informal definition of limit. I thought we'd take a minute and talk about these ideas that we have right now and then see if we can translate those into the formal definition of limit. So what I like to think of as a notion of limit, right? Just the fundamental idea is that when I see this collection of symbols, the limit as x approaches c of f of x equals L, what I'm trying to tell whoever's reading that is that the y values get really close to L when x is close enough to c without actually getting there. When the x values get close to c, the y values get close to L. And here I have a diagram that we're kind of used to. I'm going to move the camera a little bit. Can't see c down there at the bottom. There it is. If the x's get close to c, the y values get close to L. C's in my domain, and then L's talking about what the y values are doing. I do not know from this statement whether C's in the domain or not. We've seen the three different variations of this picture. One where it's exactly as I have it drawn here, one where the function value doesn't match L, and then one where I do fill in that point. All right, so I don't really know what happens exactly at C, but I know that when x gets really close to C without actually getting there, the y values get really close to L. All right, that's our notion of limit. The informal definition, suppose that f of x is defined on some open interval about c, except possibly at c itself. This is the bit that's telling me I don't know what happens at c. I don't know whether c is in the domain or not. If f of x is arbitrarily close to the number L for all x sufficiently close to c, then we say the limit of f of x as x approaches c is L, and then we write that down this way. The dots are there because I didn't write down the we say part. We say the limit of f of x as x approaches c is L, and then that's how we write it down in notation. The reason this is an informal definition is because of the arbitrarily close and the sufficiently close. Those aren't very technical terms. What do I actually mean by arbitrarily close? What do I actually mean by sufficiently close? What I said in a previous video was when I write arbitrarily close, what I mean is as close as you want it to be. I actually prefer to think of that as close as anyone could ever possibly want it to be. And then sufficiently close I like to think of as close enough. Yet still, those aren't very mathematical sounding terms. So we need to talk about what I really mean by arbitrarily close and sufficiently close. So let's say someone gives me a distance that I'm allowed to be away from L. That is a positive distance that my y values are allowed to be away. That would be my arbitrarily close. In other words, someone could say, hey, you're allowed to be this distance away from L. Are there x values I can choose that make my y values appear in that red interval on the y-axis? Okay, well I could imagine then looking at my function and saying, hey, if I pick x values in this blue region on the x-axis, well, those would all get mapped by the function into that interval. That would be my region of x's that make the y values happen there. And it's unbalanced, but that gives me an idea of what close enough, that's sufficiently close. By picking x's in here, I get y values in that little red region. So what we do is we give this distance a name. We call it Epsilon. So that symbol there is a lowercase Greek epsilon. Epsilon is just some positive distance, and it would be in reference to how far I'm allowed to go up and down. That's my arbitrarily close, some positive distance epsilon. That's how far my y values are allowed to be away from the L value. I get to sufficiently close, and what I see is there would actually be two distances. On the left, it looks like I'm allowed to go further away than I am on the right. But I want to give my reader one distance that will always work. And what I would claim is that if I take the smaller of the two distances, and I'll just call that delta, so that Greek symbol, a lowercase delta, would always work, because if I stay within that shorter distance on this side, I'm still in the blue interval. So my sufficiently close I'll represent with the positive number delta. And what I would say now is every time you pick an x value within delta of c, you will get a y value within epsilon of L. This will turn my limit definition as something that says every time you give me an epsilon that controls how far I am allowed to get away from L, I always am able to find a corresponding number delta. That's what it means for a limit to exist. When a limit doesn't exist, if you give me an epsilon, I might not be able to find a delta. So, for a limit to exist, for every positive distance epsilon, there is a corresponding number delta. I want to write that down formally as the definition of limit, but let's just do a little bit of review about distances. If I was to imagine a number line with a real number c on it, and I said, think about the interval of x values that are within some number delta, which is just a positive distance away from C. Well, what I'm really thinking about is that blue interval that I'm allowed to go to the right delta some distance and to the right, to the left that same distance delta. And what I would say is, well, I went to the right by delta, so this number here on my number line would be C plus delta. This number here on my number line would be C minus delta. And the x's in that interval would simply be the x's that were between those two numbers. That would kind of define that interval, except for the kind of, it defines that interval. C minus delta is the leftmost thing, C plus delta is the rightmost thing, and the x's I care about are in the middle. So there I have it. So let's look at that inequality just a little bit. And see if I can write it down in a more convenient fashion. I'm going to do an old inequality trick and take away C from all three parts. Another way of saying this would be to say the difference between x and c is between delta and minus delta. And this reminds me that if I satisfy that, I'm really talking about the absolute value of x minus c. I'm telling you the absolute value of x minus c has to be less than delta. And that's going to be the most convenient way of writing that down. That if I want to talk about the x values that are no more than delta away from c, what I'm saying is the absolute value of the difference of x and c is less than delta. All right, we're going to come back to this statement in just a minute. Let's see what that would look like on the y-axis. If I think about the y-axis in that same way, I would have a mark for L, and I'm allowed to go up epsilon and down some number epsilon. At the top, that would make that L plus epsilon, and at the bottom, that would make that L minus epsilon. And so the y values I want to consider are the ones between L plus epsilon and L minus epsilon. But my y values are function values, so instead of using y, let's use f of x. And doing that same thing I thought of doing before, let's take L away from all three pieces. And now I can do that same thing where I say, hey, that's a statement about an absolute value. This would be a mathematical statement that said all of my y values are supposed to be within epsilon of L. All of the y values are between L minus epsilon and L plus epsilon. The big takeaways here is if I see an absolute values statement like this, it's talking about a distance. All right, let's see if I can write down that formal definition of limit. I'll start with a nice happy picture. All right. Start with that very familiar picture that I like when we're talking about limits. I have a value c on the x-axis. I do not know anything about the function value at c, but I know my function is defined on some open interval containing c, except for possibly at c itself. On the x-axis, I have an interval where this positive distance is epsilon and this positive distance is epsilon. On the x-axis, I have an interval that I want to think about being defined by a positive distance delta. And since this is lopsided, I'm going to take the smaller value so I'm still within those two marks, so delta on both sides. One of the things you'll see in the examples I post after this is if there's a choice to make on the x-axis about delta, we always take the smaller one. We always want to be more restrictive, keeping our interval on the x-axis the ones that will give me the y's where I want them. All right, here's my formal definition of limit. No informality here, the actual definition of limit. Let f of x be defined on an interval containing c, except possibly at c itself. We say the limit of f of x as x approaches c is L, and we write that down in this fashion. If, all right, here comes the good part. For all epsilons bigger than 0, there exist a corresponding number delta bigger than 0, so that f of x minus L in absolute value is less than epsilon whenever 0 is less than x minus c in absolute value is less than delta. That is my formal definition of limit. For all epsilon bigger than 0, there exists a corresponding number delta bigger than 0, so that my y values are within epsilon of L by keeping the x values within delta of c. These are those two absolute value statements about distance. They're simply describing these two intervals. I can make the y values be arbitrarily close to L by keeping the x values sufficiently close to c. This is the mathematical formal definition of limit that can then be used to prove all of the theorems that we've seen so far. We need to see a few examples using this definition, but I'll post those in future videos. Bye for now.